okay to ask you a real quick question about the homework? Would it be all right or no?
Let's talk after.
Okay, okay.
All right. So the fun keeps coming. We do have homework to do today, and there's still more to come. All right. So last time we were laying out what some of you might say like postulates or axioms, or just what is the structure of quantum theory itself. It continues to be a challenge to see if the structure can be thought of as arising from some basic principles in the same way that Einstein relativity sort of just arises from just a few basic principles, like the speed of light is constant in all reference frames and equivalent to every reference frame. Given that, you could derive Lorentz transformations and derive it all. Whether the same thing can be said of quantum theory is another story. But with that said, let's just say what that structure is. And the way we said we're laying out that structure is to think about this from the point of view of what's commonly known as the Copenhagen interpretation, which is to say what quantum mechanics, the structure of quantum mechanics is a set of rules for doing what physics should do. And what physics should do is predict the outcomes of experiments. Okay? And of course, we can only do those predictions with some confidence. We can assign probabilities to the outcomes. So that's what we demand of our theory, that it should be able to allow us to make those predictions, assign probabilities to outcomes of measurements. And so the fundamental mathematical object in that is the state. The state is the mathematical object which allows us to do this calculation. And I've defined, although I haven't quite made this clear what I really mean by this, but it'll become clearer over the course of this week, what I mean by a pure state. Okay? Not to be confused with eigenstate. They're not the same words. They don't mean the same thing. Okay? So a pure state is a state that we would assign to the system if we have maximum possible knowledge consistent with quantum mechanics. Okay? And though if we have all the possible knowledge we can, we assign a pure state, and that pure state is a vector in the Hilbert space. Okay? Really, we can say it's a ray in Hilbert space. The overall length of the vector is something we can define to be whatever we like, and by convention we choose it to be normalized in this way. And as we discussed, that still doesn't really pin it down, because the overall phase, it says if we multiply this by any phase factor, a unit magnitude complex number, that doesn't affect in any way this. Okay? All right, so that's one object, it's the most important object in our structure. We also, although it's traditional to define this in the Copenhagen interpretation, really this is not a necessary postulate, if you like, of quantum theory. We'll come back to this over time, but let me just state what it is. What we say is that we talk about observables. These are physical quantities like energy, momentum, position, angular momentum, things that we're familiar with in classical physics, but it also includes other quantities that have no classical description of spin. And what we can say is that Hermitian operators are observable. That's to say, we can measure them. We can find out the values of these things. But the converse isn't true. There are things that are observable that are not Hermitian operators, contrary to what you might have been told. And we'll come to that. You know, we gave the example of time. Or for another example is phase of an electromagnetic wave thought of from a quantum field theory. There's no Hermitian operator for phase. But you know, we measure the phase. So, contrary to what you might have been told, there's not this one-to-one relationship between observables and Hermitian operators. All right. But what we can say is that, and again, this is not really a necessary postulate that we need to understand quantum theory, but it's something that's traditionally discussed, and so I'll put it here, and we'll see why this isn't quite a necessary postulate. But as stated, if I do a measurement of a Hermitian observable, then the results that I will see, the possible results I can see in such a measurement, are the eigenvalues of that Hermitian observable. Okay. But what is important is this, which is what we required of our theory to begin with, which is, all right, you have a state. So if the state is a pure state, and that state is then described by this vector in Hilbert space, and we've taken, unless we say otherwise, we'll always assume that we've normalized that vector. Then if we do such a measurement, and as we said, we can only find one of these eigenvalues, and if that eigenvalue is A, and that eigenvalue is non-degenerate, so there's one eigenvector corresponding to that eigenvalue, then the probability to see that result in the measurement is given by the Born rule. The Born rule is psi star psi. Okay? It's the square of the probability amplitude, right? So in this case, the state generally can be expanded in the basis of eigenvectors with probability amplitudes. This is just the square of the amplitude associated with that eigenvalue. All right? As we said, if things get a little bit more complicated, if we are looking in more general contexts. For example, suppose the eigenvalue was degenerate. Well, then it depends what the probability of seeing that result really depends on what the device is doing. Because if, for example, we know if we have a degenerate eigenvalue, then there is an eigenspace associated, spanned by all the degenerate eigenvectors, all of which that have that same eigenvalue. There's not one vector, there's an eigenspace, right? Now, whether or not to calculate the probability depends upon whether or not the measuring device knows about which of the eigenvectors which in that space we've observed. So, for example, as we discussed in previous lectures, we can fully resolve which eigenvector or a vector in that space by specifying other eigenvalues of mutually commuting observables. But if the measuring device in some sense doesn't measure what those other values are, then the probability I see is just the sum of the probabilities of all of the possible eigenvectors overlap all of the probabilities for all the different degenerate eigenvectors with that degeneracy. I sum them because I don't know which one happened. If somehow the device resolved which of these I vectors it is by specifying other quantum numbers, then it would just be one term in the sum. Okay? So it depends what's going on. What we just said, though, is we could write this in sort of a more general way by saying the probability of measuring A is this overlap, the overlap between the projection on the state and the state, where the projection is this is the projection operator, right? So if it's non-degenerate, then there's just one term, and then I get this. But if it's degenerate, and the measuring device doesn't resolve which one happened, then I have to add them all up. And of course, all the probabilities sum to 1. The total probability of having something is 1, because we've normalized that. That's equivalent to the fact that this sum of all the projectors is a resolution of the identity. Okay? Because then if I take the expectation value of this with respect to psi, I get the sum of the probabilities is 1. So another point we made last time was the fact that really what is necessary in order to define probabilities to measurement outcomes is not that I do what's called a projective measurement. And projective measurements are specified by measuring apparatuses that distinguish yes or no questions. Are you in this eigenspace, yes or no? Okay, and then you assign some probability to being in that space. And these different eigenspaces, the spaces associated with the different eigenvalues, are orthogonal, right? Because we said that the eigenvectors or eigenspaces of Hermitian observables or Hermitian operators with different eigenvalues are orthogonal. But more generally, as we will see later this lecture, any quantum measurement is defined not by a set of projectors, but a set of operators that I call E, where E are positive operators. You've seen positive operators now in your homework. Positive operators are Hermitian operators whose eigenvalues are positive numbers, well, actually not negative. Okay, but we call them positive operators. And if I have such a set of operators, such that they form a resolution of the identity, then I can assign probabilities to outcomes. This resolution of the identity, this is what has this horribly heavy-handed name that still sticks, a POVM. And what it says is that the probability of finding outcome A is this. This is a number, and because of this, and because of these two facts, these things are positive numbers that lie between 0 and 1, and thus are probabilities. And they sum to 1. So if I have such a mathematical structure, I can assign probabilities, and that's what I need. And every measurement that we could possibly do is defined by this. This is a special example. These are projection operators positive operators? What are the eigenvalues of projection operators? So if I have this, and it's some lambda, it's 1 or 0. If psi is in the eigenspace, when you project it, you get back the state. It doesn't change it. If it's not in it, and it comes back to itself, then 0. Is that clear? Okay, now of course, these are the eigenvectors. So projection operators are like yes or no answers. Are you in that space? Yes or no. They have true or false. So they're very sharp measurements. General measurements aren't that sharp. They can't be, because most devices can't resolve so perfectly, are you this or are you that? They have finite resolution. We all know that. Telescopes, what have you, they always have finite resolution. And so whatever we're doing can't always be a projected measurement. We'll see an example of that later in the lecture. But maybe you never heard about POVM, but you should. Okay? And this is the Born rule. This is the generalization of psi star psi. All right. So, a few of the things we discussed last time, I just want to reinforce these things because they're very important concepts. We talked about the expected value. Mean value, or the expectation value. And we said that if I had a state, the expected value, the mean value of an observable as given by statistics, we proved that this was equal to this. Okay? And this is equal to, for a pure state, the sum over A or A times the probability of finding A. Right? The other thing we talked about was the uncertainty. So, uncertainty is to say the following thing. I want to know how certain am I that when I do a measurement, I'm going to get the expected value. Okay? So the uncertainty, which depends on the state, is given by the square root of the variance, which is the expected value of the difference between the value and its expected value. And that's the same thing as the average of the square minus the square of the average. Okay. And what is true is that what we have is the uncertainty principle, which is easy to prove. proved in the notes and see it in other places, which says the product of the uncertainties associated with two observables. So this is really equal to the average of a squared minus average of a squared times the average of b squared times minus the average of b squared. That's what I mean when we say that, all square root. That quantity must be bigger than or equal to 1/2 the expected value of the commutator absolute value. Which says that if the two operators don't commute, the two Hermitian observables don't commute, then in general, I can't simultaneously be certain about a measurement outcome I will find if I measure A or I measure B. So the uncertainty that in my measurement outcome that I'll find in A, as measured by the RMS, is given here, and similarly for B. If, for example, the state is an eigenstate of A, what is the uncertainty in the measurement outcome of A?
I'm sorry, could you repeat that?
If the state is an eigenstate of the observable A, what is my uncertainty in what I will find in the measurement of A?
0?
0, exactly. It's an eigenstate of A. If it's an eigenstate of A, then the uncertainty is 0. Is everyone clear that why that's obviously true? Yeah, because it's a sharp value and everything. This is a definite value. There is no uncertainty. Okay. Now, suppose I measure B. Well, do I know what outcome I will find if I measure B?
Well, if it's eigenstate of A, then it will be eigenstate of B.
It depends. If it's an if it's an eigenstate of B as well, then you're absolutely correct. Then we know for sure what we'll find. But it's not true. The psi is not necessarily an eigenstate of B. Okay, if A and B commute, then we can be guaranteed. But if it doesn't commute, we don't know. But what we do know is that this uncertainty product must be bounded by this. Okay? But if A and B commute, then it's possible that my uncertainty will be 0.
It's possible but not guaranteed?
No. Right? This doesn't say. So what it says is that so here's an example.
Oh, okay.
Suppose A and B commute.
It's greater than or equal to.
Right. So this is true in this case. This is greater than or equal to 0. Now, so we said that this is an eigenstate of A. That means delta A is 0. So this holds. But it doesn't tell me what delta B is. It's possible that delta B can be 0 as well. So for example, if we had a non-degenerate eigenvalue, an A and B commute, I'll get to you in a moment, Steve. An A and B commute, then we know that psi is certainly also an eigenstate of B. But if we have a degenerate eigenvalue, then as we discussed some couple of lectures ago, that state need not be an eigenvector of B. Right? We can find there exists one, but not everyone is. So just be careful. Just because they commute doesn't mean that every possible measurement outcome is perfectly predicted with zero uncertainty for all measurements I do of those commuting observables. Yes?
Looking at the undeterminate principle, the bottom one,
Yep.
it seems that if psi is an eigenvector of A or B, then A and B either commute with each other, or the expected value of the commutator is 0 automatically.
Yes, that's correct. So if A and B commute, then this right-hand side is 0. Okay? If psi is an eigenvector of either A or B, then this left-hand side is 0, because one of these uncertainties is 0, and therefore the right-hand side will also be 0. All right, very good. So far we've talked about states, we've talked about observables, we've talked about how we calculate probabilities of outcomes and predictions of measurements. But what we haven't talked about yet is dynamics. How does the state change as a function of time? Well, here's where it gets interesting. It wasn't interesting already. There's sort of two very different dynamics that we have in quantum theory. Okay? The first is what I'll call closed system dynamics. Okay, so what do I mean by that? Well, in this case, what I mean is the following. Suppose whatever the system is completely closed off to everything else. Okay, so system is completely isolated. Doesn't mean that doesn't have lots of stuff in it. It could be, you know, a solid state material with Avogadro's number of particles in it. But it's completely isolated from everything else. Now, if it's completely isolated, we neither gain nor lose information about the system. Okay? So if that's true, if we if we started in a pure state, meaning we had maximum possible information about the system. So let's say at time t0, we assign this state. At a later time, the state is also pure, because we neither gained information, or we couldn't really, in a certain sense, nor lost information. So if we start in a pure state, we stay in a pure state. That means at a time t later, we should assign this state. So that means that what quantum mechanics says that the state at a later time is obtained from the state at an earlier time by some kind of map. There's some kind of map that takes me from time t0 to t0 plus t. This is my time evolution map. And we can ask of it some nice physical properties, like it's continuous in time. We can take this to be a differential. So if that's the case, and if this is pure, and we have neither gained nor lost information, then we didn't lose any probability of anything happening. Total probability of some outcome is still 1. That is to say, the total probability, which is the norm of the vector, the sum of all the squares of any probability amplitudes, it's got to be 1. And given this, that says the dagger of that is this. Okay, that's this vector, and this is its drop. That equals 1, which is the same thing as what it was initially. So, given that fact, that the system is isolated, and we're neither gaining nor losing information, what it says is that the time evolution map must be a unitary map. So what it says is that if we have an isolated system, the time evolution of the system must be a unitary map. Because the property of unitary operators is that they preserve the inner product. And preserving the inner product in this case means preserving the total probability. So that's one thing we can say. If the system is isolated, its evolution must be unitary. Okay. And this is a deterministic evolution. That's to say, given this, I know what it's going to be at a later time. If I know what this guy is. And physics will dictate what this is. But there's something else we know. There's another kind of way in which the state changes, or we change the state. And that's where all the contention is. So, let me get my notes here somewhere. Thank you, sir. So now we're going to come to the measurement postulate. We're going to delve into this in some detail for the remainder of the lecture. So what does the measurement postulate tell us? Okay. The measurement postulate says the typical way it's stated is as follows. If we measure the permission observable A, and we find the non-degenerate eigenvalue little a, then immediately following the state collapses, such that if I had a pure state, which was a superposition of all of these possible eigenvectors with these probability amplitudes, and I find one of them with probability given by this, then immediately after, this is the new state of the system. Okay? So what can we say? How does this kind of evolution distinguish from this kind of evolution? There's a few obviously important ways. One thing we can say, first of all, is that this is this kind of evolution is random. Because which state this goes to is not predetermined. It goes to that state with probability p sub a, depending on the Born movement. Moreover, it's kind of discontinuous. Now, what can we say about this? Well, firstly, what about the case that we described earlier in the class, where we said that the eigenvalue was degenerate? What happens then?
Increased probability.
If you don't If you're not sensitive to the different values?
Yeah.
Does it stay in the superposition?
Right, so that's a good question. So let's think about this. What about degenerate? What about the degenerate case? So let's say that psi is a sum, it's generally a superposition. Well, let's do a little bit of algebra for fun. We know we want to represent this in the basis of eigenvectors of the observable A. The way we do that is we insert a resolution of the identity, right? One way to do it. And a resolution of the identity is a sum over all the projectors, like that, right? But each projector itself is a sum over all the degenerate eigenvectors, all of which have that same eigenvalue, right? So this is a sum over A, sum over I equals 1 to the degeneracy of that. UAI, psi. Okay? So this is equal to a sum over A, sum over all vectors within that, I'll call it CAI, UAI, where CAI is the probability amplitude to be in that vector. Is that clear? So now I do a measurement. I don't know what that is yet, but we'll talk about that. And that measuring device measures the observable A and finds a particular outcome A. But it doesn't resolve, it can't tell the difference. There's nothing in the device that distinguishes which one of these U's happened. So what is the state afterwards? What do you guys think? Guys in the gender neutral sense. Yeah.
Is it just the superposition of all the degenerate states?
Exactly. So afterwards, we have this. Well, sort of. This state is not normalized. Right? Why isn't this state normalized?
Because all those C's don't add up to.
Yeah, what we had was that normalization before was that the sum over A and I of CAI squared is 1, right? But now I'm just summing over all the I for a fixed A. So I have to divide this, I have to renormalize it. Now it's normalized. So that's what happens. This we can unify this all together to say the following thing. A projective measurement, under a projective measurement, if, let's say, psi less than is the state just before the measurement, then the state just after the measurement, I'll call it t greater than, psi greater than, is what I get by projecting the state onto the eigenspace associated with that and then normalizing. This is the projection postulate, as it's sometimes called. Does this, the same thing as what we wrote down in the case of the non-degenerate situation? Let's take a look. So, suppose the state just before I measure it is this. I have non-degenerate eigenvectors. Okay, suppose that were the case. Okay? And suppose I find, measure A, find A. Now, because I'm going to say is I'm going to take this to be a dummy index, I'll call it A prime. This is a sum. I don't want, I'm finding a particular value. This is the sum over all possible values. So you shouldn't use the same symbol, okay? All right, and so there is a projector onto that, which is a one-dimensional projector. So the state just after the measurement, according to this projection postulate, is I applied this guy to this and then renormalize. And what is that? Well, according to this, this is sum over A prime, C A prime, A prime. And then I renormalize that. I just write it like that. And what's the top? The numerator. Well, this guy over here is what? It's a Kronecker delta, right? So it picks off the value where A prime equals A. So this is equal to C A divided by the norm of that. And what's the norm of this vector? Well, it's, I could write it many ways. Just have to go through this formula. You can just look at it. This is a unit vector. This is a candidate, right? So the norm is the square root of that, right? And what's the denominator then?
Absolute value of C.
Yep, so this is equal to CA divided by the absolute value of CA. So it's some phase times that, which is irrelevant. So this works for the case of a non-degenerate eigenvector. It projects onto that eigenvector, period. More generally, it projects onto the eigenspace, and then we have to renormalize it. obviously this is kind of weird, right? I mean, this thing, this idea that the state collapses. And this collapse continues to be a source of confusion and some mystery. Now, why is this, in some sense, mysterious and strange and confusing? Well, one reason is I'll tell you one of the reasons, I can tell you why I was confused when I first learned this as an undergraduate student. So, quantum mechanics is supposed to be the fundamental theory of everything, of the universe, and everything in some sense emerges out of mechanics, right? So, the measurement process itself should be described by quantum mechanics. But yet, the measurement process is doing something different than that general kind of evolution that we have in the system. Which physical situations correspond to measurement, and which kinds of physical systems are not? How do I tell the difference? And if I can't tell the difference, how do I know when to apply this rule and when I apply that rule? Let me try to be a little bit more precise about that. Suppose I have a spin, and I want to measure it. We'll talk about that in just a moment to again remind ourselves about Stern-Gerlach. And suppose I have some kind of meter. Okay. Now, why isn't it true that this together is an isolated system? In which case, the whole thing together should evolve according to a unitary evolution. After all, the meter is made up of atoms and molecules and solids and should be described. Why isn't there a joint quantum state, pure state of the whole thing, and it evolved according to unitary evolution? Versus the situation where I say, okay, I have my spin is isolated maybe, and then I peek into it and I measure it. And now it's open to this meter. Yeah, Stephen, what do you think?
Well, the first case, the isolated case, the meter's inside the isolated system and you can't observe it since it's isolated.
True. But so that's an interesting point of view. So that puts you at the center.
Well, if you're in the system as well, so you can observe it as well. The meter just on looking at the spin change the state itself.
Say that last question.
If you assume that you're in the isolated system as well, so you can observe it without disturbing it. Wouldn't the meter look at observing what state of spin it is in change the state itself?
So what we're trying to get at here is how we describe, under what circumstances do we describe, we initially there's some state of the spin, and we wanted to measure it, okay? If the rule is when you bring a meter, whatever a meter is, in contact with the spin, then the meter does some particular kind of physical thing that is no longer described by unitary evolution on the whole thing, but instead described by this.
Wouldn't the way to get around that be to have the spin somehow affect the meter without touching?
But the question is when? How does that work? I mean, under what circumstances, what does the meter have to be?
A spinometer.
But what is that? You know, in terms of being a particular amount of stuff. Yeah, see.
So, I mean, what he was saying, I was wondering too, like, so if the meter measures the spin, is that information stored in the meter
Yeah.
for you to look at later?
Yep.
So, I mean, how complicated a device does the meter have to be? Is it a simple quantum mechanical system, or is it this, you know, Avogadro's number of,
Right.
you know,
Right. So, all right, so now we come to some of the interpretations of quantum mechanics. So how does the Copenhagen interpretation deal with this problem? And this really comes to your point. What the Copenhagen interpretation would say is that what distinguishes these two kinds of evolution is that the meter, and really this is more, the meter itself is governed by different laws than quantum mechanics. The meter itself operates, according to classical mechanics. So in the Copenhagen view, in order to extract information about a quantum system, and therefore us to learn about it, we need to bring it into the macroscopic realm. That's Zeke's point about the meter being sufficiently complicated in some way, having Avogadro's number of particles. I don't know, Avogadro minus 10, Avogadro divided by 300. I don't know, but somewhere at some point, we would say that the meter is a classical object. And what it's pointing on is not a quantum uncertain state, but is actually realistic in some sense. Okay? Now, maybe there's something we could say. So this question that there's the meter itself lives in the classical world sets up a new conundrum for us. Yeah, before I get to it.
What if the meter was like a bunch of photons?
Exactly.
I mean,
So-
photons is quantum mechanical. Right?
Sure. So that's exactly the point. Where is the border between the quantum world and the classical world? At what point, if I start building up my meter with, you know, I have buckyballs, I have clusters of buckyballs, I have droplets of buckyballs, at what point does it become macroscopic enough for us to say that it's a classical meter?
When you can't observe the states anymore.
But what is it about it? What do we quantify about it that makes it say, what aspect, what's going on physically? So this question of where the quantum classical boundary lies is something, the emergence of our classical world out of the fundamentally quantum world has been one of the great pursuits, I'd say, of the last, 70 years, trying to understand, is there a quantum classical transistor? Is this a sharp transistor? What does this really mean? There is certainly true, and we will see in this course, we don't see interference between alternatives in macroscopic worlds. So there is something to be said for the fact that classical experience is different from what's predicted quantumly. And somehow that should come out of quantum mechanics in some way, if quantum mechanics. And there is, so I've set up a complete dichotomy here between what I call closed system dynamics and measurement. There's an intermediate case which might be called open quantum system dynamics. Maybe when there's part of what's going on in the meter, this thing is interacting, but some of the information is going someplace else that I don't have access to. Quantum mechanics should be able to describe that, open quantum system dynamics. And what we will see is when we have an open quantum system, interference phenomena can be washed out. And that's called decoherence. So decoherence is something important that's going on when the measurement is happening. But it still doesn't, decoherence, as we see, will not give us this. There is no way to go from a deterministic evolution to a random evolution. We have to put it in by hand. Now, if we do that, then we can ask the following question. What is collapsing? I mean the noun, not the verb. What stuff is collapsing? This comes to a point that I've kind of avoided, but now I want to address because it's an important point and one we debate right now, which is the state a physical thing? Meaning the following. Is the state like a wave on a string? A wave on waters? Or is it even something as abstract as a wave of a field? I mean, electromagnetic waves are already pretty abstract things, but we believe, or when we think about it classically, we believe that electromagnetic waves is stuff, is fields are physical things that exist. And if the state is a physical thing, and if the state collapses, then there must be a physical process which causes it to collapse. The wave becomes a delta function somehow. So if that seems inconsistent with this kind of deterministic evolution, what else could the state be? Another alternative, if yes, not if the state is the state. If yes, implies collapse is a physical process. But I'm going to give you a different example. Okay. So, what is the probability that the coin is heads up?
What kind of coin is it?
It's a quarter. Well, you don't know. So what probability would you assign to it? 50%. It's a 50-50 chance. Okay? All right, Stephen, come over here. what is the probability that it's heads up?
0.
No, look at it.
Oh, that's not tails?
That's George Washington. Look, everybody, come on. Maybe watch this later. Okay. What is the probability that it's heads up?
100%.
100%, 1. Okay? So, your state of knowledge collapsed. You previously assigned a state to the system. You assigned, because you didn't know, so if no means collapse is subjective. It's about the state is about what you know. It is a state of knowledge. Okay? And collapse means that you update your state of knowledge conditioned on what you know. Okay? And this is the Bayesian perspective on probability. This is probability assignment based on all prior knowledge. So according to Bayes' rule, suppose I have some prior knowledge, maybe it's lack of knowledge, I don't have complete knowledge, and I assign a certain probability to a certain random variable being true, p of x. So this is my prior probability that x is true. Okay, I assign that based on what I know. So for example, when I covered this up, and even if you did look at it, you still couldn't tell that was George Washington, but you assigned 50-50, for example. Now you do a measurement and you find something. You find the value y. So now I want to know what's my posterior. What is my probability of x true given that I now found y?
Probability that x given y times probability of x over probability of y.
Exactly. So this is equal to the probability that I would find y, given that x is true, times the probability that my prior probability, and then renormalized. That's Bayes' rule. So this is my prior that x was true. And this is what is called the posterior. Not my tushy, but my posterior. That is to say, the posterior probability that x is true, given that I found y. Okay? And what Bayes' rule tells me is that there's this is what's called Bayesian updating. I should update my probability assignment conditioned on a measurement result I find. Yeah?
Are those two different types of P's?
One is they're all probabilities, but this is a conditional probability, right? This is the probability that y is true given x. So these are conditionals.
So that's y depending on x being true?
Yeah. Exactly. Probability that y is true given that x is true. Yeah.
So if the wave function is that the state is not a physical thing and the collapse is subjective, then the example in the beginning of the semester with the interferometer, where we, have 100% going to 1, 0%, but just by, distinguishing the past, the changes.
Sure.
I mean,
But what it says, as we will see, and we'll continue this discussion, all measurement outcomes that happen with 100% probability, all observers must agree. Just because it's subjective doesn't mean that there aren't situations where they all have to come to the same conclusion. We'll see that. So what I want to say, and I guess we won't go much more further than this, unfortunately, but it's okay. This is really important foundational stuff, so I don't rush through this too much. Is that in some way the projection postulate looks like Bayesian updating, right? So let's say let's do this with the quantum state, okay? In quantum mechanics, so we have my prior state. That's the state I know to start with, psi less than. And the probability that x is true is given by the Moore rule. Okay? So now, what x is, I've measured some observable that has values x. Okay? Now, I want to know, so this is my prior. I do a measurement and I find y. Okay? What is the probability that x is true given that I found y? Well, according to quantum mechanics, I know how to calculate that. This is equal to the posterior state given that I found y, the probability that x is true. Okay? And the posterior state, given that I found y, is given by the projection postulate. That is, I project on y, the prior state, and I renormalize. So, according to that, this is equal to the prior state, py, px, py, prior state, divided by the prior probability that it was y. Now that looks kind of like Bayes' rule, but not exactly. In fact, if x and y are different eigenvalues corresponding to a Hermitian observable, well, this is either 0 or 1, right? Because if x equals y, well, this is 1, and if x doesn't equal y, it's 0. But as we'll see when we talk about POVMs, where these are no longer projectors, but measurements with finite resolution, this can look exactly like Bayes' rule. However, and this is where I want to conclude for the next 3 minutes, is quantum mechanics just Bayesian updating? Well, no, there's there's things in quantum mechanics that have no classical analog whatsoever. And one of them is the question of quantum disturbance or back action. On incompatible operators. So, suppose I measure an observable A. I become more certain about the value of A. If I find an eigenvalue that is non-degenerate, I become perfectly certain about it. So I gain information about A. Right? However, if A and B don't commute, then I lose information. About B. So for example, suppose at my prior state was an eigenstate of B with eigenvalue little b. My uncertainty in B is 0. Now I measure A. Now my uncertainty has been increased. And now if I measure B, I'm not guaranteed. That can't happen classically in general. So this is where the collapse is weird. The collapse isn't weird that I had an uncertainty and by measuring I reduced my uncertainty. That happens classically all the time. We do a more and more resolved measurement and we learn more and more where it is and we update what we know about that. But that shouldn't mean that I'm forced to make incompatible, non-commuting observables less certain. That's weird. That's the part of the collapse that's weird. Okay, I guess we will continue this discussion again on Thursday.